So I'm going to talk about boundary value problems for semi-linear Schrödinger equations, and to be more precise, this is the operator that we shall be considering in a bounded Lipschitz domain omega in Rn. The assumptions on the potential V are, well, it may blow up on the boundary, but not faster than the distance to the boundary to the power minus 2. This is one assumption, and the second assumption is A2 that you see here, and which I will explain in a moment. E is this inequality, which is like the Hardy inequality with respect to V, and with a constant gamma, and E is all the constants for which it holds. And the requirement is that for V itself, when gamma is equal to 1, this inequality holds. That's all. So if V is greater than or equal to 0, for instance, then the infimum of E is minus infinity, and the supremum is just the Hardy constant relative to V, which you see here. In particular, if V is gamma over the distance to some subset of the boundary F, then for V to satisfy A2, you need gamma less than this. So this is the assumption that seems a little bit mysterious in this way, but it's really very simple. Okay. Now, these two conditions, A1 and A2, imply a number of results for the Schrödinger operator Laplacian plus V. And the main ones are that the green function exists, and there is a Martin kernel KV. Now, a Martin kernel, you remember, it's a function of x and y, x in the boundary, y on the x in the domain, y on the boundary. It's like the Poisson kernel with one big difference. In the Poisson kernel, every point y in the boundary has mass equal to 1, delta y. And here, instead of delta y, you have a constant times delta y, and the constant can be anything between 0 and plus infinity inclusive. Now, there is also a ground state. I'm not going to give the definition of ground state in general. In the present case, this is just the unique positive eigenfunction of minus LV with eigenvalue lambda V greater than 0. In addition, so we have these three objects, GV, KV, and PV. The green function and the ground state are, in a way, there is an equivalence, which you see here, and which says the following, that if you keep y away from the boundary, then for x near the boundary, GVXY is equivalent to phi v. to phi vx. And with constants that are independent of y, of course, of x and y. We need a normalization, and that's the normalization. Kv and phi v are equal to 1 at a fixed point, a fixed reference point, x0 in omega. And this is the notation that we shall use all the time. Gv tau means the kernel Gv acting on a measure tau, and Kv nu means the kernel, Martin kernel, acting on the measure nu on the boundary. Of course, since we want to talk about a boundary value problem, the main question is, the main point is, how do we define the boundary trace? So the boundary trace will be defined as it is here. If u is any non-negative Borel function, then we say that trace vu, which is the LV trace of u, so we call this the LV trace of u, and we denote it by trace v. The trace is equal to the measure nu on the boundary if you have this convergence for every uniform Lipschitz exhaustion dn of omega. An exhaustion means that it's a sequence of domains that are strictly increasing and tending to omega, inside omega and tending to omega. And for any such, and Lipschitz exhaustion just means that every dn is a Lipschitz domain. In the case that this is for a non-negative Borel function, if u is a signed Borel function, we have to require in addition that the supremum of the trace of u on delta n, on the boundary of delta n, the supremum of this traces is bounded. Let's just mention that, for instance, if D is a compact subset of omega and x0 in D, then this notation dwvx0d, which you have here and here, just means the LV harmonic measure on delta D. The LV harmonic. For instance, if D admits a Poisson kernel, then this is simply the Poisson kernel times the area measure, nothing more. Okay, but of course, in Lipschitz domains, you in general don't have a Poisson kernel. In smooth domains, it's always like this. Now, properties of the trace. The trace of an LV harmonic function Kv nu is just nu. The this harmonic function is defined by a measure nu on the boundary. It turns out that the trace is exactly nu. And the trace of a potential Gv tau is always 0, provided, of course, that tau belongs to, is a measure which is finite with respect to phi v. That means that the integral of phi v d tau is finite. So the trace of this is always 0. These are very basic properties. This is a more special, interesting property. Suppose that we have a subharmonic function, LV subharmonic, I may sometimes forget to mention the LV, but when we say subharmonic in this lecture, it's LV subharmonic. This means LVW less than or equal to 0. So we have an LV subharmonic function, and we assume that, again, this condition holds. We have already seen this condition in the definition of boundary trace. So if you have this condition, then LVW, the action of LV on W gives us a measure, and this measure is in the good space, which is the space of measures tau, such that phi v d tau, the integral of phi v d tau, is finite. Of course, this is okay. All right. And trace VW, the boundary trace exists. If for every subharmonic measure, if you just have this condition, which I call condition C, then this is true. The trace exists. You'll note that by definition, if the trace exists, then this condition holds. It's part of the definition. So this essentially says that the existence of the trace is equivalent to this condition for subharmonic functions, and of course for superharmonic as well, because we don't assume anything about the sign here. Now, a corollary of this is that every subharmonic function can be represented in this way, where sigma is a measure on m delta omega, a measure on the boundary of omega, and lambda is a positive measure in omega with respect to weight phi v. And if it's superharmonic, the same, except that we have a plus sign here. The minus and plus are, of course, important because lambda is positive. Well, it's not difficult to obtain this, and I think we'll not spend time on the short proof here. This is simply a corollary of proposition 2, which tells us that LVW is a measure, a good measure, and trace VW exists. We are going to consider the boundary value problem defined here, minus LVU plus F composed with U equals tau, and trace VU, the LV trace, is prescribed, where tau is a measure in finite measure with respect to weight phi v, as you see here, and nu is a measure on M, bounded measure on delta omega. F is continuous, non-decreasing, let's say essentially increasing, and F0 is equal to 0. So F is positive, greater or equal to 0 on the positive side and of the axis, and less than or equal to 0 on the negative sides. What do we mean by a solution? Any function u in L1 log such that fu is also locally in L1 omega. And this is enough to make the equation meaningful in the distribution sense. So for such a function, we'll say that it is a solution if it satisfies the equation and if it has a boundary trace, LV boundary trace nu. This is the problem that we are going to consider. The main, this sort of problem for V equals 0, when you have just the Laplacian here, was treated in many, many papers. The point is that in general, you don't have a solution for every pair of measures tau nu. And one of the main questions is to see when do you have a solution, and of course all the usual questions: uniqueness, existence, and a priori estimates. Those have been treated for functions f under many conditions. This is not normally this is always assumed. And the various conditions have to do with conditions on the behavior of f as the argument of f goes to infinity. So the first theorem is the uniqueness. So it has two parts. First, there is a monotonicity result. You have a subsolution and a supersolution, and the boundary trace of the subsolution is dominated by the boundary trace of the supersolution. Then U1 is less than or equal to U2. That's a familiar result in various classical settings for V equals 0, and it turns out that it is true in this case too. Perhaps I'll provide an argument to show this monotonicity with respect to boundary data. Of course, once you have this result, then you immediately conclude that the boundary value problem 2 has at most one solution. It may have no solution, but if it has a solution, it's unique. So I want to describe briefly an argument for part 1 here. So U1 and U2, let's remember U1 is subsolution, U2 is supersolution, and the supersolution dominates U1 on the boundary. Now we look at, since in this situation, minus LVU plus FU1 minus FU2 must be negative. Now we use Kato's inequality, not in the original form, but in a form that applies also to measures. It's a result of Bresson-Pons, and we get here that this is less than or equal to 0. Now this term here is always positive because f is increasing, so LVU plus itself is less than or equal to 0. This means that U plus is subharmonic, positive subharmonic. Now, since it is positive subharmonic, we get a representation like this. This was in corollary 1. And Now, the boundary trace of U must be less than or equal to 0, because U1 is less than U2 on the boundary. The trace of U1 is less than the trace of U2, therefore the trace of U is negative. So we have simply U is then less than or equal to G0. We can drop this term and we have inequality. And then U plus is less than GV of the rho plus. And we know that the trace of GV of any potential, the trace of GV is equal to 0. So the trace of U plus is also 0. It's less than or equal, and it's non-negative. Therefore, as U plus is LV subharmonic, U plus must be 0. This is again by corollary 1. You see, it is subharmonic, it's positive, and the trace sigma is 0, and lambda is positive. So if W is non-negative and it's just equal to minus GV lambda, it must be 0. There is no, that's all there is to it. Okay. So this proves the result, because U plus equals 0 just means that U1 is less than U2, which we wanted to prove. And part 2 is the uniqueness is a very simple consequence. Now, another result is, well, a conditional existence result. If you have a sub-solution and a super solution of the equation, and you assume that both of them have a boundary trace. If nu1 is less than nu2, then the boundary value problem 2 has a solution for every nu, for every value, for every measure on the boundary that is between nu1 and nu2. This is again a familiar result in the case V equals 0, and usually in the case V equals 0, one looks at the boundary value problem in the setting, in the what's called the weak sense, not in the sense that we are considering it here. The weak sense of a boundary value problem is not suitable when V explodes on the boundary like 1 over delta squared. That's so we look at it in a different way, as we mentioned before, but the result still is true here. The proof is a little more tricky, but we are not going to discuss this here. There is no time. As a simple corollary, we have this. If f of GV, absolute, total variation of tau, plus total variation measure, plus KV, absolute total variation of nu, is in L. If we assume tau and nu positive, then f of GV tau plus KV nu is in L1 omega with weight phi v. if this is true, and this is something which is normally easy to check, then boundary value problem has a solution for this tau and nu. And what's the reason? Very simple. W is if we call this argument here W, then this is a super solution of the equation. You see, LVW plus FW is equal to this, which is of course greater than tau. W is of course non-negative by definition here. Minus W is a sub-solution. And so you have a solution for every tau between whose total variation is less than this, and for every nu whose total variation is less than this, in particular for every nu between nu1 and nu2. Okay, so at least we have a sufficient condition, which is actually very important. If we have additional information on F, then it's possible to obtain a much larger class of measures for which the boundary value problem has a solution. And that's rather familiar in the case V equals 0 and F power. Probably many of you have encountered such problems. Okay. If U is a solution of the boundary value problem, we said that for the definition of a solution, Fu must be in L1 log omega. Well, it can be proved that if it's a solution, it implies that Fu is in L1 omega phi v. And then you can represent the solution in this form. And I mention this because now we want to look at estimates, to obtain an estimate, an a priori estimate of solutions. Well, in view of this, estimates of the solutions will require estimates of such terms, LV potentials and LV harmonic functions. So we shall start with estimates of GV tau and KV nu. Some of the estimates that we'll encounter require an additional condition on V, which I'm going to state now. Well, I wrote it for a Lipschitz domain, but to make it easier to follow at this moment, let's assume that the domain is a smooth domain. Then V satisfies this condition that we call it condition D. If there exists A0 greater than 1 and mu greater than 0, such that for every boundary point P and every xz on the normal to P, on the inner normal to P, if delta z is, if z is much further away than delta x by the factor A0, which is something greater or equal to 1, then the ratio phi vx over phi vz is bounded by this. Now, this is a very, very mild condition. Of course, it's not monotonicity in any way. If you have here mu equals 0, then all it says is that phi vx is less than a constant times phi vz. When delta z is much larger than delta x, phi vx is less than large constant times phi vz. That's if mu equal to 0, but in general, when mu is positive, this is much larger, so that's not really monotonicity, but there is some relation to monotonicity. For instance, this condition holds. This is this example is not very interesting, but this is a good example. If you have phi v between two powers of the Laplacian, not a power, but it can oscillate between two powers, then condition D holds with mu equal alpha 1 minus alpha 2. And phi v, has this property that it oscillates between two powers of delta. For instance, when v is equal to gamma over delta squared, and gamma is a bounded measurable function in omega, which can oscillate between two values, A1, A2, smaller than the Hardy constant in omega. And the alphas are given by this. Okay, so this is an example which shows that, or at least in this example, of course, we don't have monotonicity of phi v with respect to delta, but there is a relation. It oscillates between two powers of delta. Okay. Once we have this condition, once we know this condition, we can turn to the estimates, and first the estimates of kV nu. Well, when nu is positive, the norm of kV nu with weight phi v dominates the norm of nu, and here you don't need anything more than just A1 and A2. So the norm of kV nu with weight phi v dominates the norm of nu. Since nu is positive, the norm of nu is just nu of delta omega. Now, for the bound from above, you need condition D, and we need to know that condition D holds for some mu between 0 and 1. Remember, this mu, the bound is delta z to the power minus mu, and mu in this theorem must be less than 1, greater than 0 and less than 1. Then you have also the bound from above, the norm of phi of kV with weight phi is bounded by the norm of nu. Here we don't assume, of course, that nu is positive. There is no need because this is bounded by phi v k view absolute total variation measure of nu. So there is no need to assume that nu is positive. The constants C prime depend on A, which appears, bar A appears in A1, and on omega and on mu. Bar A, let me remind you, is this here, a constant that appears in here. Okay. Okay, this we already saw. So this is the theorem. The proof is quite technical, and of course we shall not go into the proof here. I want to describe the estimates for GV. Again, U is a solution of the boundary problem. Assume that U is a solution of the boundary problem. Excuse me, I skipped this. Excuse me. These are the estimates for GV tau. The norm of tau in this space M omega phi v is phi v, the absolute value of tau. Tau is positive, so it's just d tau. So from below, we have the inequality when tau is positive. If we have in addition condition D, again for some mu between 0 and 1, then we have also the bound from above, exactly as in the result for KV. I should notice this is in both theorem 3 and theorem 4. If you know more, if we know more about phi v, then we can obtain here the estimate with a bigger weight function. For instance, if the integral of phi v, if the integral of phi v squared over delta, the integral of phi v squared over delta is finite, then we can have here the result with phi v over delta, which is a much stronger result. And there is a whole series of such inequalities. By assuming certain assumptions on the behavior of phi v, you can get stronger results here. Of course, these results are interesting only when you can exhibit interesting families of potentials V, for which phi v exhibits such behavior. So this remark applies to both the estimate for KV and the estimate for GV. Okay, now we get to the last and main point. and this is an a priori estimate for the solutions of the boundary value problem. So as we already mentioned before, if U is a solution of the boundary value problem, then Fu is in L1 omega with respect to weight phi v, and U plus GV of Fu is equal to GV tau plus KV nu. So applying the estimates that we have for GV and KV, we obtain immediately that the absolute value of U plus GVFU times phi v, the integral of this, is bounded by the norm of tau in the space M omega phi v and the norm of nu. Yeah, and one thing that we may mention here, U and, well, it will be more interesting in the next one. If U is greater or equal to 0, then we know that GV f of U phi v is bounded from below by Fu phi v. Therefore, this integral here is larger than this integral here, so we have this inequality when U is positive. For positive solutions, we have this a priori inequality, which is usually this is the strongest form of estimate that we can obtain in this context. Now, beyond this, there is, of course, a question. We know that we don't have a solution for every tau nu. It's easy to present counterexamples, but if we are given a tau nu, and suppose that no solution exists, how do we get to the good part of tau and nu? Let's say that tau and nu are positive, and no solution exists. Then the question is there any part of tau and nu for which a solution exists? So the way that we can reach that part, that would be called a reduced measure, and I'm not going to go in details about this. It's a subject for a lecture in itself, but just a few remarks. So how do we get to the good part of tau and nu when they are positive? We approximate the nonlinear terms by bounded terms. That's to say, we replace the function f, which may tend to infinity when the argument tends to infinity. We replace it by the minimum of f and n. So it will be fn is the minimum of f and n. It's not larger than n. So this will be a bounded term, and then there is a solution for every tau and every nu. You take that solution, un, and precisely with tau and nu, you take that solution un. We can show that the sequence un decreases and it converges to a solution of such a boundary value problem, but instead of tau and nu, we shall have, let's say, tau star and nu star, which are just tau star is less than tau, nu star is less than nu. Remember, I'm talking about tau and nu positive, so I get a tau star, nu star less than tau and nu. And this, it can be proved, is the good part of tau and nu. For any larger measure that is between tau star and tau, that it's strictly larger, you will not get a solution. This is the biggest part of tau and of the measures tau and nu for which there is a solution. And this is called the reduced measures for tau and nu. And there is a whole theory about this. I think that at this point, I'm not going to discuss this. And so I thank you very much, and I'm finished.
So, Moshe, you are finished, yes?
Excuse me?
You finished your talk, yes? Yes. So, colleague, so we have to discuss of this interesting talk, and maybe somebody has some question. We will begin some discussion about this talk. Maybe we will start with. I have some question. Moshe,
Yeah.
do you hear me? Yes.
I hear you. Not very well. If you could speak a little more louder.
You consider this same.
I can, of course, excuse me, I can improve this on my computer. Okay.
You consider this semi-linear equation with linear part, which is which contains this Hardy potential in semi-linear parts, f of u. But maybe it is interesting to see, and if semi-linear term has some factor which depends on x, which can degenerate on the boundary. And some question which we studied with you concerning to large solution for such a potential which may degenerate on the boundary. Maybe in this direction, maybe to develop this circle of question in this direction. What is your opinion? Because we had with Liskevich some analysis for existence of very singular solution for linear operator which has Hardy potential. But we had some conditions, we obtained it. But on my opinion, maybe it is interesting. Maybe it may be developed in this direction. What is your opinion?
Well, first of all, let me say this is. This sort of result that you are mentioning, well, we know the results of this type in the case that v equals 0, and for instance, when f is of the sort that you described. Also, in the case, there are results for the case when the trace that is prescribed is also, there is some nonlinear dependence on nu. That could be. But in this context, I haven't gone any. This is about where I am at present. This is quite new. I haven't yet published it, although it can be found on in my archive site. And so I cannot answer what you are asking. I simply don't know yet. But some of these questions I do plan to. Anyway, it would be a very interesting question to look into. And I will be very glad if other people will get into it.
Clearly. Maybe I send you this paper about this last solution for assembly linear equation with Harry potential, maybe, but more detailed about this subject. But for me, it is interesting in general sense. In what direction it may be developed, such a subject.
Okay. So I can send you a preprint very soon.
Yes.
In fact, I have already something almost. I have to make it a little nicer for presentation, but I'll send you very soon
Thank
a
you.
preprint
Yes.
of this. And indeed, the sort of question you mention is something that it's worth discussing even. It will be very interesting.
No, I plan to discuss with you this question because for me it is interesting, very, very interesting. How it depends.
We have more questions.
Yeah.
Yes, please.
Professor Dibayotti, you are welcome. Your microphone is now free. You can switch it on.
Excuse me? Could you repeat?
Professor Dibayotti would like to ask you something.
From Calcutta.
Yeah. Am I audible now?
Yes,
please. Dibayotti, please ask your question.
Yeah, I wanted to know the way, the motivation behind defining the trace using the uniform exhaustions, which seems to be a bit non-trivial to me when the trace of a basic Sobolev space functions are defined. So am I clear? Do I have to repeat my question? Do you want me to repeat my question?
So the question is, why do we use the setup with the exhaustions? Is that the question?
That's right. That's right. Yes.
Okay. The main reason is this, that, for instance, you cannot use the problems. First of all, when you set up the problems in the weak sense, you use test functions with compact support. So essentially, in that setup too, whatever you get is based on what happens in compact subdomains, because the test functions are like this. So you need that. But here you have an additional problem, that because of the strong blow-up of V on the boundary, you cannot use the weak setup. It just doesn't converge under any reasonable assumptions. So it's you are forced to replace it by this, but of course that doesn't mean that there may not be other ideas. This is a very basic idea. It's essentially, it's like this representation of the solution here is essentially a classical representation, even before the weak representation. It's the simplest possible. And this doesn't, is not affected by the blow-up of V. But you cannot have a V that blows up faster than what we are prescribed, the distance to the boundary to the power -2. If it blows any faster, then you may not have any solutions for any tau nu except so that's, and there are lots of, even in the case V equals, there are counterexamples of this nature, that if the blow-up is worse than we assume, you have no solutions for essentially any tau nu. There is another direction that is interesting here, to allow at least nu to be not a bounded measure, but a measure that can be infinity on part of the boundary. And in the case v equals 0, there is, for instance, in complex analysis, there is a lot of, just not in complex analysis even, in our, in PDE. You have a lot of, that means that you allow U to blow up on the boundary or on part of the boundary. Okay, that would be very interesting here too. What I described here is just the case when tau and nu is bounded, and tau is bounded relative to the weight function phi v. So that's certainly a restricted case.
Okay. Also, one small question: that are these solutions in the very weak sense?
Are these again? Could you repeat?
Yes.
Yeah. Are these solutions in the very weak sense?
I'm sorry, my hearing is not very good, and I don't understand.
I was asking that whether the solutions are in very weak sense.
Very weak sense.
Very weak sense. Well, they are only in the sense that that is described here. Only in the sense that is described here. No, I don't know if they are in a, well, that could be. There is, as you all point out, there is a big family of questions for continuing this. And all these questions have not yet been investigated. I don't really know of any previous work in this, with this type of boundary data. So all of these are interesting questions. In some of them, I'm sure I will be interested to also to look further, and anybody can go on with this.
Thank you very much. Thank you very
much. Please question, additional question.
Excuse me?
Please. Please.
We have one more question from Irina Filimonova. Irina, your microphone is on now. Would you like to ask it in voice, or I can just read your question?
Yeah. You, what?
Just a second. Irina Filimonova writes, please show me the slide with formulas 6 and 7 again. 6 and 7.
What is 6? Here.
Yes, and she asks, are there inequalities in the formulas in different directions?
Yeah, one is for, what do you mean? Yes, one is the estimate from below, and one is the estimate from above.
Yeah.
What's the question? I didn't understand it.
Ира, у вас микрофон можно включить.
What?
Irina, do you hear us? Probably something is wrong with her microphone, because we already stopped to block it, but she says nothing. Okay.
What? I'm sorry, I cannot follow the...
Does not respond. Let us consider that she asked whether, well, correctly. So she asks whether one inequality estimates the norm of V from above, and another inequality estimates the same norm from the opposite direction. Yes.
The answer is yes. Okay. Yeah.
Thank you very much.
Thank you. Thank you for repeating the question for me.
I see no more questions.
Dear colleague, who would like to ask some essential question, because it was very interesting and attractive talk, and I believe that it generates many interesting questions. Please don't hesitate to ask our friends. As I understand, nothing more. So, Professor Marcus, please, we would like to ask you to send to say to thank you again for your very interesting talk. You attract very many attention. I get that our people, our mathematicians, will attract their attention to this interesting question, to this interesting subject. It is main success for our conference.
Yes, thank you very much for your
yes,
words, and I'll send you a preprint, and perhaps we can discuss it further.
Yes, I will continue. Yes, of course.
Some related problems. Yes. Sure. Thank you.
Very nice. Very nice. Very good opportunity to contact. It is very good opportunity to speak in internet and to have such conferences online. Thank you. Thank you very much.
Okay. All the best.